Extended periodic table. An extended periodic table theorizes about chemical elements beyond those currently known in the periodic table and proven up through oganesson, which completes the seventh period in the periodic table at atomic number 118. If further elements with higher atomic numbers than this are discovered, they will be placed in additional periods, laid out to illustrate periodically recurring trends in the properties of the elements concerned. Any additional periods are expected to contain a larger number of elements than the seventh period, as they are calculated to have an additional so-called G block, containing at least 18 elements with partially filled G orbitals in each period. An 8-period table containing this block was suggested by Glenn T. Seaborg in 1969. The first element of the G block may have atomic number 121, and thus would have the systematic name unbionium. Despite many searches, no elements in this region have been synthesized or discovered in nature. According to the orbital approximation in quantum mechanical descriptions of atomic structure, the G block would correspond to elements with partially filled G orbitals, but spin-orbit coupling effects reduce the validity of the orbital approximation substantially for elements of high atomic number. While Seaborg's version of the extended period had the heavier elements following the pattern set by lighter elements, as it did not take into account relativistic effects, models that take relativistic effects into account do not. Pekka Paikko and Burkhard Fricke used computer modeling to calculate the positions of elements up to z equals 172, and found that several were displaced from the Madelung rule. As a result of uncertainty and variability in predictions of chemical and physical properties of elements beyond 120, there is currently no consensus on their placement in the extended periodic table. Elements in this region are likely to be highly unstable with respect to radioactive decay and undergo alpha decay or spontaneous fission with extremely short half-lives, though element 126 is hypothesized to be within an island of stability that is resistant to fission but not to alpha decay. Other islands of stability beyond the known elements may also be possible, including one theorized around element 164, though the extent of stabilizing effects from closed nuclear shells is uncertain. It is not clear how many elements beyond the expected island of stability are physically possible, whether period 8 is complete, or if there is a period 9. The International Union of Pure and Applied Chemistry defines an element to exist if its lifetime is longer than 1014 seconds, which is the time it takes for the nucleus to form an electron cloud. As early as 1940, it was noted that a simplistic interpretation of the relativistic Dirac equation runs into problems with electron orbitals at Z1/alpha 137, suggesting that neutral atoms cannot exist beyond element 137, and that a periodic table of elements based on electron orbitals therefore breaks down at this point. On the other hand, a more rigorous analysis calculates the analogous limit to BZ173 where the 1 subshell dives into the Dirac sea, and that it is instead not neutral atoms that cannot exist beyond element 173, but bare nuclei, thus posing no obstacle to the further extension of the periodic system. Atoms beyond this critical atomic number are called supercritical atoms. Heavier elements beyond the actinides were first proposed to exist as early as 1955, and were called superheavy elements. The first predictions on properties of undiscovered superheavy elements were made in 1957, when the concept of nuclear shells was first explored and an island of stability was theorized to exist around element 126. In 1967, more rigorous calculations were performed, and the island of stability was theorized to be centered at the then undiscovered Fliravium. This and other subsequent studies motivated many researchers to search for superheavy elements in nature or attempt to synthesize them at accelerators. Many searches for superheavy elements were conducted in the 1970s, all with negative results. As of December 2018, synthesis has been attempted for every element up to and including unbiseptium, except unbatrium, with the heaviest successfully synthesized element being oganesson in 2002 and the most recent discovery being that of tennessine in 2010. As some superheavy elements were predicted to lie beyond the 7-period periodic table, an additional 8th period containing these elements was first proposed by Glenn T. Seaborg in 1969. This model continued the pattern in established elements and introduced a new G-block and superactinide series beginning at element 121, raising the number of elements in period 8 compared to known periods. These early calculations failed to consider relativistic effects that break down periodic trends and render simple extrapolation impossible, however. In 1971, Fricke calculated the periodic table up to Z equals 172, and discovered that some elements indeed had different properties that break the established pattern, and a 2010 calculation by Pekka Paikko also noted that several elements might behave differently than expected. It is unknown how far the periodic table might extend beyond the known 118 elements, as heavier elements are predicted to be increasingly unstable. Glenn T. Seaborg suggested that the highest possible element may be under Z equals 130, while Walter Greiner predicted that there may not be a highest possible element. There is currently no consensus on the placement of elements beyond atomic number 120 in the periodic table. The table below shows one possibility for the appearance of the 8th period, with placement of elements primarily based on their predicted chemistry. All of these hypothetical undiscovered elements are named by the International Union of Pure and Applied Chemistry's Systematic Element Name Standard, which creates a generic name for use until the element has been discovered, confirmed, and an official name approved. These names are typically not used in the literature, and are referred to by their atomic numbers. Hence, element 164 would usually not be called unhexquadium, but rather element 164 with symbol 164, or E164. At element 118, the orbitals 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f, 5s, 5p, 5d, 5f, sixs, 6p, 6d, 7s and 7p are assumed to be filled, with the remaining orbitals unfilled. A simple extrapolation from the Aufbau principle would predict the 8th row to fill orbitals in the order 8s, 5 grams, 6f, 7d, 8p, but after element 120, the proximity of the electron shells makes placement in a simple table problematic. Although a simple extrapolation of the periodic table, following Seaborg's original concept, would put the elements after 120 as follows: 121 to 138 form the G-block superactinides, 139 to 152 form the F-block superactinides, 153 to 161 would be transition metals, 162 to 166 post-transition metals, 167 equals halogen, 168 equals noble gas, 169 equals alkali metal, 170 equals alkaline earth metal. Dirac-Fock calculations predict that it will most likely go 121 to 142 form the G-block superactinides, 143 to 156 form the F-block superactinides, 157 to 165 form the transition metals, 166 to 170 post-transition metals, 171 equals halogen, 172 equals noble gas. Not all models show the higher elements following the pattern established by lighter elements. Pekka Paikko, for example, used computer modeling to calculate the positions of elements up to Z equals 172 and their possible chemical properties. He found that several elements were displaced from the Madelung energy ordering rule as a result of overlapping orbitals. This is caused by the increasing role of relativistic effects in heavy elements. He predicts that the orbitals will fill up in this order: 8s, 5 grams, the first two spaces of 8p, 6f, 7d, 9s, the first two spaces of 9p, the rest of 8p. This corresponds to elements 119 and 120 being alkali and alkaline earth metals, 121 to 138 G-block superactinides, 139 and 140 post-transition metals placed below thallium and lead, respectively, 141 to 155 F-block superactinides, 156 to 164 transition metals, 165 and 166 alkali and alkaline earth metals below 119 and 120 and opening period 9, 167 to 168 below 139 and 140, and 169 to 172 completing period 8. He also suggests that period 8 be split into 3 parts, 8a, containing 8s, 8b, containing the first 2 elements of 8p, and 8c, containing 7d and the rest of 8p. Fricke's predictions up to element 184 also found some elements to be displaced from the Aufbau principle as a consequence of relativistic effects. He predicted that after element 120, a long transition series characterized by the filling of 5 grams and 6 f orbitals would begin, and continue until element 154. A 5th transition metal series in which 7d orbitals are filled then would contain elements 155 to 164, and the 8th period would possibly end there. It is also possible that element 157 is in fact the first 7d transition metal, another shift resulting from relativistic effects. Elements 165 and 166 were predicted to be alkali and alkaline earth metals, though they may also mix characteristics of groups 11 and 12 and instead be placed below rankinium and copernicium, respectively. Finally, elements 167 to 172 would be the heaviest members of groups 13 to 18. Fricke initially proposed that elements 165 to 172 would constitute a 9th period, as these elements may follow a similar pattern to periods 2 and 3 and have no transition metals. Due to overlapping orbitals and possible mixing of group characteristics in superheavy elements, element 172 may instead close period 8, however. The period 8 elements up to unbiseptium, except unbatrium, have had synthesis attempts. So far, none of these synthesis attempts have been successful. The synthesis of ununonium was first attempted in 1985 by bombarding a target of Einsteinium-254 with calcium-48 ions at the Super HILAC accelerator at Berkeley, California. No atoms were identified, leading to a limiting cross-section of 300 Nb. Later calculations suggest that the cross-section of the 3N reaction would actually be 600,000 times lower than this upper bound, at 0.5 pb. As ununonium is the lightest undiscovered element, it has been the target of synthesis experiments by both German and Russian teams in recent years. The Russian experiments were conducted in 2011, and no results were released, strongly implying that no ununonium atoms were identified. From April to September 2012, an attempt to synthesize the isotopes 295 UUE and 296 UUE was made by bombarding a target of berkelium-249 with titanium-50 at the GSI Helmholtz Center for Heavy Ion Research in Darmstadt, Germany. Based on the theoretically predicted cross-section, it was expected that an ununonium atom would be synthesized within 5 months of the beginning of the experiment. The experiment was originally planned to continue to November 2012, but was stopped early to make use of the 249Bk target to confirm the synthesis of Tenney's sign. This reaction between 249Bk and 50Ti was predicted to be the most favorable practical reaction for formation of ununonium, as it is rather asymmetrical, though also somewhat cold. Nevertheless, the necessary change from the silver bullet 48Ca to 50Ti divides the expected yield of ununonium by about 20, as the yield is strongly dependent on the asymmetry of the fusion reaction. Due to the predicted short half-lives, the GSI team used new fast electronics capable of registering decay events within microseconds. No ununonium atoms were identified, implying a limiting cross-section of 70 Fb. The predicted actual cross-section is around 40 Fb, which is at the limits of current technology. The team at the Joint Institute for Nuclear Research in Dubna, Russia, is planning to begin new experiments on the synthesis of ununonium and unbinylium using the 249Bk plus 50Ti and 249Cf plus 50Ti reactions in 2019 using a new experimental complex. The team at Riken in Japan also plans to make attempts on these elements around the same time with 248 cm targets using the 248 cm plus 51V and 248 cm plus 54 Cr reactions. Following their success in obtaining oganesson by the reaction between 249CF and 48Ca in 2006, the team at the Joint Institute for Nuclear Research in Dubna started similar experiments in March-April 2007, in hope of creating unbinyllium from nuclei of 58Fe and 244Pu. Isotopes of unbinyllium are predicted to have alpha decay half-lives of the order of microseconds. Initial analysis revealed that no atoms of unbinyllium were produced, providing a limit of 400 Fb for the cross-section at the energy studied. The Russian team planned to upgrade their facilities before attempting the reaction again. In April 2007, the team at the GSI Helmholtz Center for Heavy Ion Research in Darmstadt, Germany attempted to create unbinyllium using uranium-238 and nickel-64. No atoms were detected, providing a limit of 1.6 Pb for the cross-section at the energy provided. The GSI repeated the experiment with higher sensitivity in 3 separate runs in April-May 2007, January-March 2008, and September-October 2008, all with negative results, reaching a cross-section limit of 90 Fb. In June-July 2010, and again in 2011, after upgrading their equipment to allow the use of more radioactive targets, scientists at the GSI attempted the more asymmetrical fusion reaction. It was expected that the change in reaction would quintuple the probability of synthesizing unbinyllium, as the yield of such reactions is strongly dependent on their asymmetry. 3 correlated signals were observed that matched the predicted alpha decay energies of 299UBN and its daughter 2950G, as well as the experimentally known decay energy of its granddaughter 291LV. However, the lifetimes of these possible decays were much longer than expected, and the results could not be confirmed. In August-October 2011, a different team at the GSI using the Tosca facility tried a new, even more asymmetrical reaction. Because of its asymmetry, the reaction between 249CF and 50Ti was predicted to be the most favorable practical reaction for synthesizing unbinyllium, although it is also somewhat cold. No unbinyllium atoms were identified, implying a limiting cross-section of 200 Fb. Jens Volker Kratz predicted the actual maximum cross-section for producing unbinyllium by any of these reactions to be around 0.1 Fb. In comparison, the world record for the smallest cross-section of a successful reaction was 30 Fb for the reaction 209 by 278 Nh, and Kratz predicted a maximum cross-section of 20 Fb for producing the neighboring ununanium. If these predictions are accurate, then synthesizing ununanium would be at the limits of current technology, and synthesizing unbinyllium would require new methods. The team at the Joint Institute for Nuclear Research in Dubna, Russia, is planning to begin new experiments on the synthesis of ununanium and unbinyllium using the 249Bk plus 50Ti and 249Cf plus 50Ti reactions in 2019 using a new experimental complex. The team at Riken in Japan also plans to make attempts on these elements around the same time with 248 cm targets using the 248Cm plus 51V and 248Cm plus 54Cr reactions. The synthesis of unbinyllium was first attempted in 1977 by bombarding a target of uranium-238 with copper-65 ions at the Gesellschaft für Schwerionenforschung in Darmstadt, Germany. No atoms were identified. The first attempts to synthesize unbibium were performed in 1972 by Flerov et al. At the Joint Institute for Nuclear Research, using the heavy ion-induced hot fusion reactions. These experiments were motivated by early predictions on the existence of an island of stability at n equals 184 and z 120. No atoms were detected and a yield limit of 5 Nb was measured. Current results have shown that the sensitivity of these experiments were too low by at least 3 orders of magnitude. In 2000, the Gesellschaft für Schwerionenforschung Helmholtz Center for Heavy Ion Research performed a very similar experiment with much higher sensitivity. These results indicate that the synthesis of such heavier elements remains a significant challenge and further improvements of beam intensity and experimental efficiency is required. The sensitivity should be increased to 1 FB in the future for more quality results. Another unsuccessful attempt to synthesize unbibium was carried out in 1978 at the GSI Helmholtz Center, where a natural erbium target was bombarded with xenon-136 ions. In particular, the reaction between 170Er and 136Xe was expected to yield alpha emitters with half-lives of microseconds that would decay down to isotopes of flerovium with half-lives perhaps increasing up to several hours, as flerovium is predicted to lie near the center of the island of stability. After 12 hours of irradiation, nothing was found in this reaction. Following a similar unsuccessful attempt to synthesize unbionium from 238U and 65Cu, it was concluded that half-lives of super-heavy nuclei must be less than 1 microsecond or the cross-sections are very small. More recent research into synthesis of super-heavy elements suggests that both conclusions are true. The two attempts in the 1970s to synthesize unbibium were both propelled by the research investigating whether super-heavy elements could potentially be naturally occurring. Several experiments studying the fission characteristics of various super-heavy compound nuclei such as 306UBB were performed between 2000–2004 at the Flerov Laboratory of Nuclear Reactions. Two nuclear reactions were used, namely 248 cm plus 58 Fe and 242 Pu plus 64 Ni. The results reveal how super-heavy nuclei fission predominantly by expelling closed-shell nuclei such as 132SN. It was also found that the yield for the fusion-fission pathway was similar between 48Ca and 58Fe projectiles, suggesting a possible future use of 58Fe projectiles in super-heavy element formation. Scientists at GANL attempted to measure the direct and delayed fission of compound nuclei of elements with Z equals 114, 120, and 124 in order to probe shell effects in this region and to pinpoint the next spherical proton shell. This is because having complete nuclear shells would confer more stability on the nuclei of such super-heavy elements, thus moving closer to the island of stability. In 2006, with full results published in 2008, the team provided results from a reaction involving the bombardment of a natural germanium target with uranium ions. The team reported that they had been able to identify compound nuclei fissioning with half-lives 1018s. This result suggests a strong stabilizing effect at Z equals 124 and points to the next proton shell at Z 120, not at Z equals 114 as previously thought. A compound nucleus is a loose combination of nucleons that have not arranged themselves into nuclear shells yet. It has no internal structure and is held together only by the collision forces between the target and projectile nuclei. It is estimated that it requires around 1014s for the nucleons to arrange themselves into nuclear shells, at which point the compound nucleus becomes a nuclide, and this number is used by IUPAC as the minimum half-life a claimed isotope must have to potentially be recognized as being discovered. Thus, the GANL experiments do not count as a discovery of element 124. The fission of the compound nucleus 312,124 was also studied in 2006 at the Tandem ALPI Heavy Ion Accelerator at the Laboratorio Nazionale di Legnaro in Italy. Similarly to previous experiments conducted at the JINR, fission fragments clustered around doubly magic nuclei such as 132SN, revealing a tendency for super-heavy nuclei to expel such doubly magic nuclei in fission. The average number of neutrons per fission from the 312,124 compound nucleus was also found to increase, confirming that the trend of heavier nuclei emitting more neutrons during fission continues into the super-heavy mass region. The first and only attempt to synthesize unbipontium was conducted in Dubna in 1970–1971 using zinc ions and an americium-243 target. No atoms were detected, and a cross-section limit of 5 Nb was determined. This experiment was motivated by the possibility of greater stability for nuclei around Z126 and N184, though more recent research suggests the island of stability may instead lie at a lower atomic number, and the synthesis of heavier elements such as unbipontium will require more sensitive experiments. The first and only attempt to synthesize unbihexium, which was unsuccessful, was performed in 1971 at CERN by René Bimbot and John M. Alexander using the hot fusion reaction. High-energy alpha particles were observed and taken as possible evidence for the synthesis of unbihexium. Subsequent unsuccessful experiments with higher sensitivity suggest that the 10 MB sensitivity of this experiment was too low, hence, the formation of unbihexium nuclei in this reaction is highly unlikely. The first and only attempt to synthesize unbiseptium, which was unsuccessful, was performed in 1978 at the Unilac Accelerator at the GSI Helmholtz Center, where a natural tantalum target was bombarded with xenon-136 ions. A study in 1976 by a group of American researchers from several universities proposed that primordial superheavy elements, mainly livermorium, unbiquatium, unbihexium, and unbiseptium, could be a cause of unexplained radiation damage in minerals. This prompted many researchers to search for them in nature from 1976 to 1983. A group led by Tom Cahill, a professor at the University of California at Davis, claimed in 1976 that they had detected alpha particles and X-rays with the right energies to cause the damage observed, supporting the presence of these elements. In particular, the presence of long-lived unbiquatium and unbihexium nuclei, along with their decay products, at an abundance of 10 to 11 relative to their possible congeners uranium and plutonium, was conjectured. Others claimed that none had been detected, and questioned the proposed characteristics of primordial superheavy nuclei. In particular, they cited that any such superheavy nuclei must have a closed neutron shell at n equals 184 or n equals 228, and this necessary condition for enhanced stability only exists in neutron-deficient isotopes of livermorium or neutron-rich isotopes of the other elements that would not be beta-stable, unlike most naturally occurring isotopes. This activity was also proposed to be caused by nuclear transmutations in natural cerium, raising further ambiguity upon this claimed observation of superheavy elements. On April 24, 2008, a group led by Amnon Marinov at the Hebrew University of Jerusalem claimed to have found single atoms of unbibium-292 in naturally occurring thorium deposits at an abundance of between 1011 and 1012 relative to thorium. The claim of Marinov et al. Was criticized by a part of the scientific community, and Marinov says he has submitted the article to the journals Nature and Nature Physics, but both turned it down without sending it for peer review. The unbibium-292 atoms were claimed to be superdeformed or hyperdeformed isomers, with a half-life of at least 100 million years. A criticism of the technique, previously used in purportedly identifying lighter thorium isotopes by mass spectrometry, was published in Physical Review C in 2008. A rebuttal by the Marinov group was published in Physical Review C after the published comment. A repeat of the thorium experiment using the superior method of accelerator mass spectrometry failed to confirm the results, despite a 100-fold better sensitivity. This result throws considerable doubt on the results of the Marinov collaboration with regard to their claims of long-lived isotopes of thorium, runconium, and unbibium. It is still possible that traces of unbibium might only exist in some thorium samples, although this is unlikely. The possible extent of primordial superheavy elements on Earth today is uncertain. Even if they are confirmed to have caused the radiation damage long ago, they might now have decayed to mere traces, or even be completely gone. It is also uncertain if such superheavy nuclei may be produced naturally at all, as spontaneous fission is expected to terminate the R process responsible for heavy element formation between mass number 270 and 290, well before elements heavier than unbinylium may be formed. A recent hypothesis tries to explain the spectrum of Przybylski's star by naturally occurring flerovium, unbinylium, and unbihexium. Element 118, oganesson, is the last element that has been synthesized. The next two elements, elements 119 and 120, should form an 8 series and be an alkali and alkaline earth metal respectively. Beyond element 120, the super-actinide series is expected to begin, when the 8 electrons in the filling 8p1/2, 7d3/2, 6f5/2, and 5G7/2 subshells determine the chemistry of these elements. Complete and accurate CCSD calculations are not available for elements beyond 122 because of the extreme complexity of the situation. The 5 grams, 6F, and 7D orbitals should have about the same energy level, and in the region of element 160, the 9s, 8p3/2, and 9p1/2 orbitals should also be about equal in energy. This will cause the electron shells to mix so that the block concept no longer applies very well, and will also result in novel chemical properties that will make positioning these elements in a periodic table very difficult. For example, element 164 is expected to mix characteristics of the elements of group 10, 12, 14, and 18. The first two elements of period 8 will be ununonium and unbinylium, elements 119 and 120. Their electron configurations should have the 8s orbital being filled. This orbital is relativistically stabilized and contracted, thus, elements 119 and 120 should be more like rubidium and strontium than their immediate neighbors above, francium and radium. Another effect of the relativistic contraction of the 8s orbital is that the atomic radii of these two elements should be about the same as those of francium and radium. They should behave like normal alkali and alkaline earth metals, normally forming +1 and +2 oxidation states respectively, but the relativistic destabilization of the 7p3/2 subshell and the relatively low ionization energies of the 7p3/2 electrons should make higher oxidation states like +3 and +4 possible as well. The superactinide series is expected to contain elements 121 to 157. In the superactinide series, the 7d3/2, 8p1/2, 6f5/2 and 5g7/2 shells should all fill simultaneously. This creates very complicated situations, so much so that complete and accurate CCSD calculations have been done only for elements 121 and 122. The first superactinide, unbionylium, should be a congener of lanthanum and actinium and should have similar properties to them. Its main oxidation state should be +3, although the closeness of the valence subshells energy levels may permit higher oxidation states, just as in elements 119 and 120. Relativistic stabilization of the 8p subshell should result in a ground state 8s28p1 valence electron configuration for element 121. In contrast to the ds2 configurations of lanthanum and actinium. Its first ionization energy is predicted to be 429.4 kJ/mol, which would be lower than those of all known elements except for the alkali metals potassium, rubidium, cesium, and francium. This value is even lower than that of the period 8 alkali metal ununonium. Similarly, the next superactinide, unbibium, may be a congener of cerium and thorium, with a main oxidation state of +4, but would have a ground state 7d18s28p1 valence electron configuration, unlike thorium's 6d27s2 configuration. Hence, its first ionization energy would be smaller than thorium's because of the greater ease of ionizing unbibium's 8p1/2 electron than thorium's 6d electron. The collapse of the 5 grams orbital itself is delayed until element 125. The electron configurations of the 119 electron isoelectronic series are expected to be 8s1 for elements 119 through 122, 6f1 for elements 123 and 124, and 5g1 for element 125 onwards. In the first few superactinides, the binding energies of the added electrons are predicted to be small enough that they can lose all their valence electrons. For example, unbihexium could easily form a +8 oxidation state, and even higher oxidation states for the next few elements may be possible. Unbihexium is also predicted to display a variety of other oxidation states. Recent calculations have suggested a stable monofluoride UbHef may be possible, resulting from a bonding interaction between the 5 grams orbital on unbihexium and the 2p orbital on fluorine. Other predicted oxidation states include +2, +4, and +6. +4 is expected to be the most usual oxidation state of unbihexium. The superactinides from unbipentium to unbiennium are predicted to exhibit a +6 oxidation state and form hexafluorides, though UBPF6 and UBHF6 are predicted to be relatively weakly bound. Stable monofluorides of these elements may also be possible. The bond dissociation energies are expected to greatly increase at element 127 and even more so at element 129. This suggests a shift from strong ionic character in fluorides of element 125 to more covalent character, involving the 8p orbital, in fluorides of element 129. The bonding in these superactinide hexafluorides is mostly between the highest 8p subshell of the superactinide and the 2p subshell of fluorine, unlike how uranium uses its 5f and 6d orbitals for bonding in uranium hexafluoride. Despite the ability of early superactinides to reach high oxidation states, it has been calculated that the 5 grams electrons will be most difficult to ionize. The UB6+ and UB7+ ions are expected to bear a 5G1 configuration, similar to the 5F1 configuration of the NP6+ ion. Similar behavior is observed in the chemical INA.